Hello YouTube, this is Jay Coder back with another stream, and today I found a interesting video that I wanted to look at and also go over with you guys, and I think we'll be able to learn some good things from this video. It's about from the Android developer YouTube channel. It's about building an app from scratch, and let's see what they have to say about the guidelines and specifications and rules and how we can learn from the pros. Alright, without further ado, let's get started with the video. Like and subscribe to this channel, and yeah.
Hello, I'm Don, and I'm an engineer on the Android Developer Relations team. Today, I'm going to show you how to build a scalable, modularized, testable app from scratch. Now, this won't be a Hello World app. I'll concentrate on building an app architecture which will enable your app to grow. We'll use modules to separate responsibilities and create a test infrastructure to verify that your app behaves as expected. Lastly, we'll look at how to build a flexible, intuitive, and great-looking user interface. I'll be covering a lot of different concepts, so if I cover something you're not familiar with, there's a link on virtually every slide which will take you to more information about the current topic. Throughout this talk, I'll use the Now in Android app as an example. The source code is available on GitHub. In the app, we have a screen which shows content which is customized for you. It displays a list of news articles and allows the user to bookmark each article. We're going to take a look at how the For You feature was built, starting with how bookmarks work. The architecture for a feature like this can be broadly divided into two layers, UI and data. The data layer obtains and exposes app data to the UI layer, as well as performing business logic. The UI layer displays app data on screen and reacts to any changes in that data. An important word here is reacts. By setting up a stream of data between the layers, we are creating a reactive UI. It just needs to be told how to update its state when new data arrives. It's important to understand that the UI does not request or poll for data, it just collects data. The only communication which happens in the opposite direction are events. The data layer handles these events, updating its underlying data and emitting any changes back to the UI. In this way, we have a single source of truth for the app's data, and the data only flows in one direction. This is known as unidirectional data flow and is an excellent way of keeping your app in a consistent state. If we apply this general guidance to this specific feature, we can clearly define the responsibilities for each layer. The data layer should store user bookmarks and expose them to the UI layer by publishing a stream. We can do this using Kotlin flows. The UI layer then displays this information and updates it whenever it changes. The UI should also provide a way for the user to add and remove bookmarks, and these user events are passed back to the data layer so the data can be updated. Let's dive into the data layer to see the individual classes which we should implement. The data layer has two types of component: repositories, which expose the app data and centralize changes to that data, and data sources, which obtain data from a single source. Let's take this from theory to reality by implementing the classes in the data layer. We'll start by implementing a local data source class. This will store bookmarks locally on the device using Jetpack Data Store. Let's take a look at the code. Local data source accepts a data store object as a dependency. We then convert to a list of bookmarks using the map function. The most important concept to understand here is that we're not pulling data directly from data store. We're merely setting up the stream of data and mapping each item in that stream to a format which clients of this class can use, in our case, a list of strings. Lastly, it provides a function to update bookmarks by adding or removing them from a map backed by data store. Each time the bookmarks change, a new list of bookmarks is emitted into the bookmark stream flow. We can now add a repository to expose these functions to the UI layer. The code in the bookmarks repository is pretty simple. It takes our local data source as a dependency and exposes the bookmark stream and toggle bookmark function from it. If we were doing something more complicated, like combining data from multiple data sources, this would be the place to do it. A common example is an offline first feature which pulls data from a network data source, then synchronizes it with a local data source. We also need some news articles to display, and obtaining these can be implemented in much the same way. The only difference being that the data comes from the network rather than being stored locally. We can add a network data source to pull news articles from a REST API, and a news repository to expose those news articles to the UI layer. It's good practice to have a repository for each type of data in your app. So that's our data layer sorted. Now our UI layer needs to display those bookmarks next to each news article and let the user add and remove bookmarks. Let's take a look at the UI layer in more detail. Here we also have two component types. The state holder handles the screen logic and constructs UI state from app data. It does this by listening for changes in the data layer. And the screen displays that UI state using UI elements. Again, applying this general guidance to our feature, we can define the responsibilities for each layer and the classes we need to create. Let's take a look at the state holder. For this, we can use a Jetpack view model, prefixing the name with for_u, the name of this feature. This class listens for data from the news and bookmarks repositories and combines them to create a UI state. Before we dive into the code, let's look at exactly what's happening here. We have lists of news resources coming from our news repository, and we have lists of IDs coming from our bookmarks repository. Our view model combines these two to create a list of savable news resources. Each item in this list contains the news resource itself and or not. The code for these models is pretty simple. News resource has some fields for the news article like its ID and title, and savable news resource is just a wrapper around news resource which also includes whether that news resource is bookmarked. It's used by our UI layer to represent the combined data from both the news and bookmarks repositories. And here's the code for our view model. We accept the data repositories in our constructor and create a combined data variable to store a flow of savable news resources. This is created using the combine function, which, as its name suggests, combines the data streams from our two repositories. Whenever the data changes in either stream, our transformation function is called with the latest news resources and bookmarks. Inside it, we map each news resource to a savable news resource, checking to see whether it's bookmarked. Let's go back to our view model diagram for a second. Once the data is combined, our view model needs to convert this to a UI state, which can be one of two possible values: loading or success. Loading is used when data is being initially loaded, usually when the news resources are being loaded over the network. And success is used when the data has been loaded successfully. It contains the list of savable news resources so the UI can display them. Here's the code which does that. We use a sealed interface to represent the two UI states. Loading is just an object, whereas success is a class which holds the savable news resources. In our view model, we create a variable to expose our UI state as a state flow. This is a flow which can have an initial value and is optimized for sharing state. To convert our combined data into a UI state, we simply map the list of savable news resources into the success UI state. To convert the combined data flow into a state flow, we use state_in. We specify the coroutine scope which the flow should be started in, and an initial value of loading. Collecting from flows can be expensive, especially if they access the network or sensors. We can use the started parameter to indicate that we only want the flow to be active when there is at least one collector, usually a screen. This avoids wasting resources. When the last collector unsubscribes, we wait 5 seconds before stopping the upstream flow, just in case the collector only went away temporarily, as can happen during a screen rotation. This avoids the potentially time-consuming operation of restarting the flow. The final task our view model should perform is to handle requests from the UI to save and unsave bookmarks. We do this by creating a toggle bookmark function. Inside it, we call the relevant method on the bookmarks repository and execute that call from the view model scope. Now, one of the benefits of using a view model is that it survives configuration changes. This means that operations initiated using the view model scope will continue to run and our UI state will be preserved. Okay, it's time to display something on screen. For this, we create, you guessed it, a for_u screen. This will read the UI state from the view model and render it using UI elements. We'll use Jetpack Compose for this, as it's the recommended UI framework for new apps. Let's refresh our memory on what the design for this feature looks like. We can see that the news articles are displayed in a column, and the design concept for each article is known as a card. So let's go ahead and create a draft implementation for our UI. First, we create a composable function for the news resource card. It takes the news resource, its bookmark state, and a lambda which we call. Also create a composable to display a list of these news resource cards called newsfeed. It simply creates a column and iterates through the elements, rendering a news resource card for each one. Now, you can preview composables in Android Studio using the app preview annotation. Here's how our newsfeed looks currently. Okay, it isn't going to win any design awards, and we're certainly not matching the design spec yet, but don't worry, we're going to fix this shortly. Now let's create the For You screen. This accepts the current UI state and a lambda to call when the user taps on any of the bookmark buttons. When the UI state is loading, we just display the text loading, and for the success state, we get the news resources from the UI state and pass them to the newsfeed along with the lambda to be called when the user adds or removes a bookmark. So, how do we get our UI state? Well, we can create a stateful version of For You screen, which obtains our view model, and once we have it, we can use collect_as_state with lifecycle to collect from the stream only when the app is in the foreground to avoid wasting resources, and to convert the stream into a composed state. When the UI state changes, it causes any composable functions which has read it, like our For You screen, to be recomposed. Once we have the UI state, we simply supply it to our stateless For You screen, along with a reference to any events which the screen needs to call, in our case, just the toggle bookmark function. So, why don't we just have a single stateful For You screen? Well, as we'll see later, stateless functions are easier to test and to preview. In a Compose app, we still need an activity. This is the glue between the Android framework and your Compose code, and is what shows your UI to the user. We try to keep our activity as simple as possible, just calling setContent and then our UI code. Okay, so we've created classes for the UI and data layers. We could just place all these classes inside the app module, but we know that our app is going to do more than just display news articles. By creating modules for each distinct set of responsibilities, we can make our codebase more scalable. Modules can also enable parallel working and potentially reduce build times. Here's the modularization strategy we used in the Now on Android app. At the top level, we have app modules, which are responsive modules. These are scoped to a single area of user-facing responsibility, such as providing the content for the For You screen. Feature modules do not depend on each other, but can depend on core modules. These are common library modules used throughout the app, also scoped to a single area of responsibility. For example, repositories are held in the data module and networking code in the network module. Let's figure out where our classes should go. Our main activity goes into our app module. Classes which are specific to the For You feature are moved into the For You feature module. Data classes, which are used by other modules, are moved into the core model module. For repositories into core data, classes associated with local storage using data store move into core data store, and network classes move into core network. Now, a common problem with modularization is that you end up with lots of duplicate dependencies and configuration blocks inside your build files. We solved this in Now on Android using a feature called convention plugins. The idea is to move common options and dependencies into a plugin, and then include that plugin in all the modules which require those options. This way, all your configuration stays in one place and can be easily updated. The plugins and supporting code is contained within a separate build logic module, which is built before any other module. This ensures that any configuration changes are propagated to all dependent modules before they're built. Another common problem in modular codebases is keeping track of library versions, especially when they're scattered through multiple Gradle files. Version catalogs is a Gradle feature which solves this. A version strategy helped us to build a loosely coupled graph of modules for Now on Android, enabling us to work in parallel and reduce the amount of time deciding where to put new code. You don't have to modularize from the outset, but if you know your project needs to scale, you can save a lot of time by introducing a modularization strategy early. So at this point we know what classes to create and which modules to save them in. What we don't know for sure is whether our code functions as intended. Tests can do this by verifying the behavior of individual classes and our app as a whole. They allow us to add new features or refactor our codebase with the confidence that if we break something, we'll know about it before our product is shipped to users. In fact, if you have a clear idea of the classes you need to create, it's even better to write the tests first, but it's up to you to decide when to write tests, just as long as you actually write them. There's a lot of theory behind testing, which you can check out using the link below. I'm just going to show you how we can write a unit test and a UI test to verify the behavior for our feature. We should add tests wherever there is logic, and one of the places there's a lot of logic is in our view model. As we've seen already, it combines data from two streams and converts it into UI state. Let's write a unit test to verify this behavior. The first thing we need to do when writing a test is isolate the test subject from its dependencies, in this case the repositories. Instead of using the real repositories, which are going to be operations like pulling data from the network, create test dependencies, also known as test doubles. This allows us to control the inputs to our test subject and verify the output, plus our tests will run a lot faster. The problem is our view model depends on concrete classes. We should rename any concrete classes and have them implement an interface which the test subject can then depend on. This way we can create test classes which will be supplied when testing. Let's implement our view model test class. We start by creating a rule which sets our coroutine dispatcher to a test dispatcher. This ensures that any coroutines are executed sequentially inside our test and is essential when testing flows. Then we set up the dependencies and create a variable to hold the subject under test, the view model. And we ensure that it's recreated with our test. The view model produces the correct UI state. Inside our test, we start collecting from the view model state. Without this, no values would be emitted into the flow. We tell our test news repository to send some news resources to the view model, and our test bookmarks repository to toggle a bookmark for the first news resource. Now we get our UI state. We then check that it's success and the correct news resource has been bookmarked. Lastly, we cancel the collection job, otherwise the test will run indefinitely. Since this is a locally run unit test, we save it in the test folder in our feature module. A test for our screen in a UI test. Here we have a choice. We can either run the UI test directly on our host using a testing framework like Roboelectric. This is known as a local test and is saved in the same location as our previous test. Or we can run it on a device or emulator running Android, known as an instrumented test. Local tests generally run faster but offer less fidelity than instrumented tests. Let's create an instrumented test for our screen. First, we add a JUnit rule which allows us to control composables. Now we create a test which will verify that the news articles are displayed. The setContent method and have it save it in the Android test folder. Now that we know that everything is working as intended and we have a solid infrastructure in place, let's make our app look better. The Material Design System provides a framework and set of guidelines for creating compelling, consistent, and intuitive user interfaces. It includes a set of customizable UI components for Jetpack Compose. Material 3 is the latest version of Material Design, and our design team has given us a beautiful design spec based on this, including colors and typography. We can use these to define a theme for our app. Any Material Design components we use will be styled according to our theme. Let's take a look at this in action. We take the colors from our design spec and define them in code. Then we define a color scheme for light and dark modes. Material 3 gives each color a semantic name which describes the context in which that color should be used. For example, the on-primary color will be used when on top of the primary color. We can also create a typography class to specify our text styles. Again, Material 3 gives us a set of names to clearly define the role for each text style. With our colors and text styles defined, we can now create a theme composable which wraps all the content in our app. First, we decide which color scheme to use based on whether the device is in dark mode. Then create a material theme based on our color scheme and typography. To use the theme, we simply wrap our content in our theme composable. If we preview our news resource card, we can see that the button is now using the colors we defined in our theme. We can specify our text styles whenever we render text, and we can take advantage of other material design components, like the card, which adds rounded corners by default and derives colors from our theme. One of the great things about material design components is that they're designed to be customized. In Now on Android, we customized several of the stock components and created a design catalog app, which ships as part of the project so everyone on the team can easily see the UI components they have to work with. A good example is the toggle button class. It wraps the material icon button to provide extra features, like the circular button. Bookmark button then wraps toggle button to provide the bookmark icons for the on and off states. Now, if we swap our normal button for the bookmark button, add some padding, and an image using an image loading library like Coil, we'll start to get much closer to our design spec. Okay, we made it. We learned how to implement a scalable architecture and modularize our codebase, as well as add tests to verify our app's behavior. Lastly, we learned how to use material design with Jetpack Compose to create beautiful, intuitive apps. But wait, this talk only covers the very basics of these topics, and there's some important ones which I haven't covered, which you should definitely check out, including navigation, dependency injection using Hilt, performance testing, and designing for all screen sizes. The Now an Android app includes all of these features, so be sure to check it out. Thanks for watching.
All right. I hope that helped you guys out. And I'll include more information about the source code in the description. And I appreciate you guys watching. And until next time, always stay coding. Peace.